I'm happy to welcome Guy van Broeck. I'll introduce him. He's an assistant professor at UCLA, where he runs a statistical and relational artificial intelligence lab. He is a recipient of many awards, many best paper awards. He also recipient of NSF Career Award, the Sloan Fellowship, and the Ichikaya Computer and Thought Award, which is a very prestigious award. So I think I'll give the floor to Guy, and please, we are happy to have you here.
Thank you, Nina. Thanks for the invitation. Let's see if I can share my screen. Hope you see everything well. All right. Yeah, thanks for inviting me. And so I kind of want to give an overview about what people in my lab have been doing, trying to do some reasoning about the probabilistic behavior of classifiers. And it will be mostly kind of explainable AI, but I also try to sneak in a little bit of kind of verification of neural networks. So hopefully that will be interesting for everyone. And feel free to interrupt with questions if you have any. It's always nicer for a Zoom talk. Okay, so this is kind of roughly, I think, how I see the field, but also many other people see the field now, right? We have this kind of tension between the old way of doing AI and then the flashy new way of doing AI, the pure logical way, and then the pure kind of end-to-end deep learning way. And you know, maybe 5 to 10 years ago, you know, the left-hand side here was often being dismissed as just you know, just logic. But it's really good at some things, right? It's at slow thinking, being deliberative, cognitive, model-based to do extrapolation. And it has some amazing achievements, and this community certainly knows. But, you know, it's often dismissed as just being brittle because of the noise, uncertainty, and incomplete knowledge not being handled very well. And then maybe 5-10 years ago, we thought, oh, there's this kind of new way of doing AI, which is purely learning based. It's doing fast thinking very well. It's super instinctive, perceptive, model free, and great at doing interpolation. And of course, it also has these great achievements. But I think maybe in the last 2-3 years, everyone kind of came to realize that, yeah, this approach to AI is also brittle, just like the logical approach was brittle. And the reason, of course, is that you have all these issues, which is why we're here today for this series of talks. Not just with explainability and verification, but also with algorithmic fairness, adversarial attacks, unknown unknowns, distribution shifts, etc., etc. And the way that I look at this problem is that you know, these problems exist because we fail to incorporate some reasonable, sensible model of the world that allows us to reason about what we've learned. And so this is kind of what drives my research in the last few years. And so for today, I'll give you a few kind of ideas related to this bigger picture that kind of find some synthesis between learning and reasoning. So we're going to use some reasoning tools to improve what the learner can do. And specifically, I'll talk about explainability, of course, which is the main focus today, I presume, but also verification. And but then also mention some other works on algorithmic fairness and on handling missing data in machine learning, which are also very related in the techniques that will help us address these issues. Okay, so that's kind of the big picture. So concretely, what I'll talk about today is 3 kind of big things. So first, I'll start with something purely theoretical, and I apologize if you're not theoretically inclined. I'll try to make it intuitive, but it's about the tractability of SHAP. And so SHAP is a particular type of explanation, which some folks may have talked about before today. I'm not sure. I'll briefly introduce it, and then we'll study, you know, when can we actually compute these SHAP explanations. And so this will be a motivation for us because unfortunately the answer will be you can almost never compute them efficiently. So this will be our motivation to go to kind of develop more tractable models that allow us to reason about the behavior of classifiers more efficiently. And so I'll introduce that framework, which will be centered around probabilistic circuits. And then I'll give 3 different kind of applications in this bigger picture. This will be about handling missing data and about algorithmic fairness. And so these I'll just go over very briefly because they're not the focus of today. And then I'll spend most of the time going into one application of this kind of general framework and coming up with probabilistic sufficient explanations. And so these will be explanations that give some probabilistic guarantees about what the classifier will do on certain types of instances. And then if I have any time left in the end, as a dessert, I'll do something that has nothing to do with explainability, but is about neurosymbolic verification. Specifically, I'll mention some things we've done around learning monotonic neural networks. And this is, I think, a great example of combining reasoning and CP and SAT with neural networks, because here we have actually an SMT solver getting state-of-the-art results in neural network training. So I will hopefully briefly mention that type of work. Okay, so first thing on the agenda is the theoretical motivation, and I'll tell you about this work here with Anton, Max, and Dan. Okay, so this is not new to anyone here. We have the problem of explainable AI. We're asking the bank, can we get a loan? Bank says no loan, and so this is not great. What we would like is some explanation. And so slightly more formally, we actually send our feature vector X to the bank. The bank has a classifier, and the classifier will now not just give me a prediction, f of x, but also some kind of explanation. Okay, and you've seen a bunch of these today, but we'll specifically for this discussion talk about SHAP explanations. So what are SHAP explanations? So they're a feature-based attribution score, meaning that you will actually look at this feature vector, and you will learn that the reason why you would get a loan is your age, but the reason why you wouldn't get a loan is the debt that you have collected. And so here you can tell for every feature roughly how much it influenced the actual outcome and the decision by the bank. And what's nice about SHAP explanations is that they're based on shapely values from game theory, which are a kind of very traditional way to measure the influence of certain variables on an outcome. They're really nice because they're model agnostic. They really don't care what your function is. They're very intuitive, as I hopefully will explain on the next slide. And most importantly, they're a big deal in practice. So you'll go to the GitHub repository of SHAP explanations, and it has 11,000 stars and almost 2,000 forks. And this was like maybe 6 months ago. So these are really widely used by people in industry, for example. So how do they work? So the intuition is that you're going to pretend that you're going to look at these features one by one. And you will at some point have to make a decision based on seeing only part of the set of features. And once you see that part of the set of features, you will try to compute what would I predict to be the loan amount, or what would I predict to be my decision after seeing these features one by one. So here's a particular order. And so this is arbitrary. I say I'm going to first look at the first feature, which is the age of the applicant, then at the second feature, which is their debt, and so on and so on. And so now the importance of this variable x2, or its contribution to the decision, is really the difference between just before seeing x2 and just after seeing x2, what will be my prediction f. What's crucial here is that there's an expectation here. If I only see one feature, I see the age of the person, I cannot really tell whether I will give them a loan or not. So I have to kind of assume something about these other features in expectation and see what would I expect to be the decision for the loan. And so this difference here tells us, after adding x2 to what I know about this person, how much does it change the outcome? Okay. And again, feel free to interrupt with any questions if anything's unclear. All right, so then this tells us what is the importance of x2 for this particular order pi, but we don't really have a natural order on these features, right? I could have first looked at the debt and then at the age or some other permutation. And so what the SHAP score says is that the importance of this feature x2 is really the average over all of these contributions here for these random orders. Okay, hope that makes sense. So it's a very intuitive definition, very nice and relatively simple, and it's nice black box, doesn't care what f is, and so on and so on. Okay, so now the challenge is, how do we compute these explanations, right? So this is one of those explanations that actually has a formal definition. As you saw it on the previous slide. So we can ask, what is the, how difficult is it to come up with this explanation? And lots of algorithms have been proposed for SHAP. Some of them are approximate, some exact, some are claimed to be efficient. And it also kind of depends on the machine learning model, whether you can make this efficient. But when we started doing this work, there was considerable confusion about the tractability of this. It wasn't really clear for these algorithms that were out there whether they were in fact exact and correct and efficient, or if the approximations that were proposed, if they were actually necessary, or whether these problems could be solved efficiently anyway. And one example of this confusion is the tree SHAP algorithm, which is quite influential, which was proposed first as an exact algorithm, but then later users found that it was not actually computing the SHAP score, it was computing something different. So the question is, could you actually fix this? Could you compute the SHAP score for, in this case, a decision tree or a random forest? Okay, so we investigated this theoretically. And to do this, you first have to kind of figure out what are the moving pieces, right? And the first moving piece, of course, is the actual machine learning model, the hypothesis space of the machine learning model. And so here we looked at kind of anything we can think of: linear regression, random forests, neural networks, naive Bayes, logistic regression, all sorts of Boolean functions, and so on. And so the answer is going to be different depending on what this class of functions is, because some of them may be easy to explain, some of them may be hard to explain. So the second moving piece, which is often ignored, unfortunately, people don't really explicitly talk about it, is the data distribution. I told you that when we compute these SHAP scores, we have to say, if I only know the age of the applicant and I don't know all the other features, what do I expect to be the decision? Well, that's an expectation that requires a probability distribution to fill in the missing features from the feature vector. Okay, and so here we looked at three reasonable choices that are all really simple. One fully factorized distribution. And so this is often done in practice. People just say, you know, these missing features, I don't know what they are, so I'll just independently flip a coin for all of them if I need to kind of guess what their value would be. Okay, very simple distribution for the feature vector. Another reasonable option is to use a simple graphical model or standard kind of probabilistic model in AI, or to use the data distribution, to just say, I will look at the training data that I have, and I will just pretend that this is the distribution over all the possible feature vectors. And so now I can compute expectations with respect to this data distribution here. I'll go into more details about all three of these. Okay, so let's quickly look at these theoretical results, and I don't want to belabor them because maybe some of you are not really into the theory part of this, but I just want to give you the takeaway messages of when we can compute these explanations. So one of the key results that we found is that if you want to explain with SHAP a classifier under a fully factorized data distribution, where for all of these missing features I will just flip a coin and then kind of guess, what would be these unknown values, then computing the SHAP explanation of a classifier is just as hard as computing the expectation of this classifier under the same distribution. Meaning that if I can just guess what would be a random person's loan decision, then I can also compute SHAP and vice versa. These two things are equally difficult from a computational complexity point of view. So that's good news in one sense, because that means that whenever we can compute an expectation of a classifier, whenever we can just say for a random person, a random applicant, this is my prediction, then we can also do SHAP. So this means we can do this, we can compute SHAP for linear regression, decision trees, random forests, certain types of Boolean functions. And so there, computing explanations is nice and efficient. But this kind of equivalence works in both directions. And there's also a bunch of problems for which we know that computing the expectation of the classifier is computationally hard. You will not be able to do it as far as we currently know. And so for those problems, finding an explanation of those classifiers is actually going to be impossible computationally as well. And so here we show that for things like neural networks with sigmoid activation functions, all sorts of general Boolean functions, things that are very simple like naive Bayes, or even logistic regression, which is, you wouldn't even think twice about, would it be difficult to explain logistic regression? It's such a simple type of classifier. Well, it turns out computing the SHAP explanations of logistic regression with something as simple as a fully factorized distribution is sharply hard. It's computationally intractable. And so this is kind of interesting, especially the logistic regression result here, because again, you wouldn't really expect such a simple type of classifier to be intractable to explain with SHAP. So I want to maybe give a little bit of a intuition for why is it so difficult to compute these SHAP explanations of something as simple as logistic regression. And here I want to kind of give a dummy proof using a simple example. And so the reduction goes from the number partitioning problem. And so quick reminder, number partitioning problem is a problem where you're given some set, like the set here of these 4 numbers, and you would like to partition this set into 2 parts that each sum to the same number. And so these are 2 subsets here that together form the original set, and they both sum to 4. So this is a solution to the number partitioning problem, okay? And unfortunately, counting such partitions is sharply hard. Right? I cannot, if I give you a long list of integers, you won't really efficiently be able to know, worst case, how many of such partitions there are that are a solution to this number partitioning problem. So this is on the one hand, but we were interested in logistic regression, a very simple machine learning model, and we would now like to show that this is also very hard to do SHAP on. And so here's how the reduction goes. So just pretend that I have this logistic regression function that, just to recall, it's a linear function of your features that is pushed through a sigmoid function. Okay, that's logistic regression. And the numbers here, they look very similar to these integers we had earlier, they're just a little bit larger. Okay, kind of multiplied everything with a large number, and I also subtracted a large number. And I did this very carefully in such a way that anytime I give an input that corresponds to a non-partition, for example, I select the first, second, and third element. This is not a solution to the number partitioning problem because 1 plus 2 plus 2 is 5. That's not 4, which is half of, or 5 is not equal to 3. So this is not a solution to my number partitioning problem. I also have this other solution, which is the complement. Here I just turned every 1 into a 0 and every 0 into a 1, which is also not a solution to my number partitioning problem. If I plug in these 2 feature vectors into my logistic regression classifier, then for one of them, the first one in this case, the prediction will be almost 1. And that's because the sigmoid will, for a very large number, become 1. The other number has to be close to 0 in that case. Because if this is a very large number, then this has to be a very small number. And the sigmoid will predict a 0. Okay? And this is interesting because this means that for these solutions that are, for these inputs that are not solutions of the number partitioning problem, half of them will give a positive label and the other half will give a negative label. So the expected decision for your loan or whatever is actually 50%. Okay? But there's only one caveat, which is that some of these inputs actually correspond to solutions to the number partitioning problem. For example, here, this is the example I had earlier, selecting the first and the third element versus the second and the fourth element. These are these 2 feature vectors. If I plug these 2 feature vectors in, then you can verify later, both of my predictions will actually be 0. And this is always going to happen for a solution to my number partitioning problem. And so this means that I can see what is my expected prediction of my logistic regression function, and I can see how much probability mass is missing from 0.5. And this number tells us exactly how many partitions there are after some scaling. And so this is hopefully intuitively for some of you a simple reduction proof showing that the expectation of a logistic regression function is sharply hard to compute. And this implies that computing SHAP explanations of logistic regression is also sharply hard. Okay, so this was the most theory that I'll do today. Hopefully that was okay. otherwise interrupt me with questions. I'll very quickly tell you what happens if you have other types of distributions. Right, so the real world is really not a fully factorized distribution. You don't just flip a coin for every feature. That's not kind of the type of applicants you get at your bank. They're not just completely random features. They actually, there's some interesting relationships between all these features. And, here we could say, let's just assume that the features form some interesting distribution represented by a graphical model. And here you could take something as simple as naive Bayes, a very simple probabilistic model, a classifier that's completely trivial. Just predict one of the variables, x1, to be the decision for your loan. Okay, there's nothing simpler that you can come up with almost than this combination of a classifier and a distribution. And unfortunately, we also proved that computing SHAP explanations even here is NP hard. And so this is really a kind of bad news. Everything's intractable once you have a more interesting assumption about how your features relate to one another. Okay, so trivial function classes do not really help us here. And then the last setting you may be interested in is, what if I just do what I'm comfortable with as a person who likes to do sampling? I just take some training data sampled from the true data distribution. I don't care to actually have it available to me as a graphical model or a Bayesian network or anything like that. I'll just look at the table. And this is interesting because, this should be easier, right? If I just have a bunch of examples of my applicants for my bank, surely there's just very few of them, right? There's a finite number of them, whatever, 1 million. And most of these, things that are not samples, they are impossible. So I don't really have to take them into account when computing my SHAP explanations. And so these empirical distributions that come from a training set, they should be easy to work with. There's a very few number of possible worlds. Unfortunately, even there, computing SHAP explanations, even of of any function almost is sharply hard. And this also means that the problem, remember where we were motivated by this tree SHAP algorithm, which had this bug, this problem cannot be solved. This bug cannot be fixed unless sharp P is in P. You will not be able to actually do what they did because they were actually considering something related to this setting, right? They were trying to build a SHAP algorithm for this setting, claiming to be exact and efficient, which turned out to be impossible. Okay, so that's all the bad news for today. There were a few cases where you could compute SHAP. If you had a fully factorized distribution, which again is not realistic at all. This is not what your data looks like. And if you were lucky enough to try to explain one of these classifiers here shown in green, everything else is intractable. Most notably, things like logistic regression are intractable for SHAP to explain in any setting we could think of. Therefore, also neural networks and so on. Okay. All right, so that's the summary of this kind of motivation part. Again, feel free to interject with questions. Okay, so I hope you're now sufficiently motivated to ask this question. How can we then reason about these classifiers under some non-trivial assumptions about these feature vectors, right? If I want to think of realistic images or realistic applicants for my loan, how can I tell what the classifier does if even these simple things cannot be done efficiently, right? So, and this is part of what motivates my research. So next part, we'll try to come up with some solutions that are at least sometimes efficient. And to do this, I'll have to give you some background on something called probabilistic circuits. And we'll use those to build solutions to some of these problems. Okay, so now I'll give a little bit of background on these probabilistic circuits. And it's not super important that you get everything. It's just to give you the high-level picture of why they're different and interesting from some of the other models of data distributions that you've maybe seen before. Okay, so this here is some alphabet soup of a bunch of probabilistic models that we may want to use to think about our feature vectors before they go into our classifiers. And some things you may recognize here are things like GANs or variational autoencoders, kind of popular generative models of what our data looks like. But there are also more traditional things here, like Bayesian networks, like naive Bayes. And there's some things that we'll be using a lot, like arithmetic circuits and some product networks. And so the distinction between some of these and the others is that the ones that are shown in red here, they're all intractable. So they suffer from the same issues that I mentioned in the previous part of the talk, is that almost anything you would like to do with these types of models of our feature vectors will not be efficient. And so we would like to actually use some of these models here that are tractable. We will be able to use them to compute probabilities efficiently and even compute things like SHAP explanations or other things efficiently, right? And I'll give you, without again going into too much detail, I'll give you some quick sense of how these things work through this unifying framework of probabilistic circuits. And I really don't have, maybe I shouldn't be presenting this because I don't actually have time to explain it to you in a way that you'll fully appreciate it. But let's just kind of get the high level, okay? So these probabilistic circuits, they look like this. They're kind of like neural networks. And you can read them like, here is the input. This is my feature vector. And here is the output, which is the probability of this particular data point. And of course, this will be important, not just to give a probability to all these SHAP feature vectors, but also to many other types of probabilistic inference tasks. Okay, so the input here are going to be very simple distributions, things like a univariate Gaussian or a Bernoulli coin flip, or something that's very easy to deal with. So what we'll do is we'll try to combine these using products and sums. And these product nodes, they represent factorizations. Kind of similar to this fully factorized distribution of coin flips I showed earlier, we'll just say the probability of a larger feature vector is just the product of the probabilities of the pieces of this vector. Okay, but we know that this is not a very interesting distribution, not a very realistic one. So you kind of combine these product nodes with some nodes that are mixture models. They're saying that, oh, this feature is actually distributed as a mixture of Gaussians, for example. And so that's like a weighted sum of simpler distributions. And now the trick is that if you nest these as a kind of deep neural network, you get very, very expressive complex distributions. And you can still evaluate them as a neural network. So here I have a simple probabilistic circuit. I have a feature vector that I would like the probability density of. So I compute the probability density of each of these input Gaussians. And I just take weighted sums and products until I get my probability density at the output. Okay, so this is kind of like a neural network that outputs for you a probability. So why are these tractable models? Why do we use them to reason about the behavior of classifiers? Well, we can compute certain things that would otherwise be intractable, like a marginal probability. I could ask, sum over all of the possible worlds, all of the possible feature vectors, and sum up all their probabilities, or for a subset of them. And so here, I will skip over these slides because I think I won't have enough time. But essentially, the way it works is that you have to assume some properties of these circuits, which allow you to push the integration problem through these nodes. So instead of computing the integral of my distribution, I compute the weighted sum of integrals. And this is for a sum node. For a product node, you will also assume something, namely that these are all independent coin flips or distributions. And then I can also take my integration problem and turn it into a product of integrals. And this means that I can now actually use dynamic programming to evaluate any marginal probability. I can compute integrals here at the input, which are either 1 if I integrate out this variable, or if I observe the variable's value, could be here some probability density. And then all I have to do is take sums of products of these integrals to get my marginal probability at the output. And this is super hand wavy, but I hope you at least kind of get the general framework. And so we'll be using these things because we can build algorithms around them that allow us to compute things efficiently. Okay, second point is these things are not only tractable, you can compute things efficiently with them, they're also very expressive, some of them. And here, this is again, just to quickly convince you, if you compare these probabilistic circuits that have been learned on data sets with standard approaches for learning distributions, including autoregressive neural networks, variational autoencoders, you see that their behavior is essentially on par with these deep generative models. The only difference is that here you can compute a probability efficiently in these circuits, and in these other models, it would be intractable to do so. So just hopefully trust me, these things are actually really good at fitting your data while also getting you probabilities very efficiently. Okay, so this is kind of the summary of this piece of background. You have a lot of models in AI to represent these distributions over feature vectors. Some of them are very tractable. Things like naive Bayes are really easy to compute a probability in. However, they're not very expressive. You won't be able to really fit your data very well. Things like a fully factorized distribution also live here, right? They're very tractable, but very bad models of your data. Then you have these very, very expressive models of your data, usually built around neural networks, GANs, variational autoencoders, but you won't be able to get a probability out of them that's exact and efficient. And so these other models, which we call probabilistic circuits as an umbrella term, they kind of live up here. And these are the things we'll build our tools around. Okay. So if you want to know more, check the slides on my website. There's a link to a tutorial, which is a 3-hour tutorial, which explains everything, how you learn these things, and properly explains what I explained very poorly. There's also an overview paper, kind of a survey, kind of introduction tutorial paper, which you can find on my website. And if you like to play with code, there's also a Julia library that kind of trains these models on the GPU for you, et cetera, et cetera. Okay, so that was a quick piece of background. And now let's see what we can do with these things, right? We would like to now solve some of these problems around machine learning, things like missing features, fairness, explainability, try to address them using the ability to reason about these feature vectors and then how they affect what the classifier will do, okay? And the first thing I want to mention is this work on reasoning about missing features. This is joint work with Pasha, Yuchang, Itao, and Antonio. So in this work, we would like to deal with the issue where you train a machine learning model, and suddenly when you deploy it in your hospital, maybe you no longer have this test available, maybe the machine broke down, maybe someone didn't fill out the survey. And so you have some missing data at prediction time that you couldn't account for when you were training the model. And so in a standard machine learning setting, now your model has become useless. You have to fill in some value for these features, otherwise you won't be able to get your prediction out. And so the way that we think about this problem, excuse me. So the way that we think about this problem is as an expectation, similar to the expectation you saw in the SHAP definition. We would like to consider all the possible ways in which one could have filled out these question marks. You know, what are the possible values of these unknown variables? And you would like to compute the probability of each of these missing values, given the ones that we have observed, right? Because these things depend on each other. If you know my country, the country I'm from, then you may also know how many taxes I pay or whatever, right? And we would like to know what would actually be the output of our classifier had we known all of these missing features in expectation. Okay, so this is very similar to the expectation we had when we were computing SHAP, but now we're using it to handle missing data at prediction time. So how can this ever be tractable? I just told you that a bunch of things are impossible, right? And now it turns out that if your feature distribution, this distribution P here, if this is a probabilistic circuit, and this function F here is what we call a regression circuit. You can think of it as, it could be many different things. It could be, in fact, something like logistic regressions, log odds, or it could be random forests. I won't go into the details of all the functions that are supported here, but if these are somehow compatible, then you can do this efficiently. And you can build an algorithm that computes this expectation in closed form exactly and in polynomial time. And I just want to kind of give you, again, the intuition, how it works. It's very similar to how I showed you how you compute a marginal probability. You kind of look at the root nodes, the output layer of your neural network, and you kind of decompose the task into simpler tasks one layer down in the circuit. And so here, if you want to compute the expectation of a function m with respect to a distribution n that are both represented as these circuits, these probabilistic circuits, in a slightly different syntax, all you have to do is look at all kind of combinations of 1 and 3, 1 and 4, 2 and 3, 2 and 4, and do some dynamic programming in order to evaluate the circuit in quadratic time. And this will get you these expected predictions very efficiently. So all you really need to do is learn a classifier that you can turn into one of these circuits. For example, a random forest is fine. And you also have to train a probabilistic circuit, which I earlier convinced you can really do very well at fitting your data and can really capture all the dependencies between these features. And now you can compute their expectation. So how does this do in practice? Well, here you see on some classification data sets, things like MNIST, Fashion MNIST. As data goes missing, standard techniques for this problem start to deteriorate in performance. So here you have some imputation techniques, and they start to really perform quite poorly. But computing these expected predictions actually gets you relatively high accuracy for a long time, even as features go missing. Similarly, in regression data sets, here lower is better. Here we compare to things like mice or other kind of multiple imputation methods. And again, computing these expected predictions will actually get you the best predictions under missing data. Okay, so that was a quick kind of detour around missing data. You can do all sorts of other cool stuff with this. For example, if you're the insurance company, you would like to know, is my predictive model biased by gender? If I take a random feature vector belonging to someone who identifies as male or female, what will be the difference in the predicted amount for the insurance? And here you see that females are, according to this particular insurance price prediction model, supposed to pay $900 more in insurance, right? So then you can find these issues with your model as you reason about how is my learned function expected to behave on some subset of my population described by these properties. Okay, so now that we're talking about fairness, I also want to briefly mention this other work, which is also a way that we reason about the probabilistic behavior of classifiers, which is about finding latent fair decisions. And this is work with Yu Zhang and Mei Wang. And so here the goal is to actually learn a classifier from some features that are sensitive or not sensitive. So sensitive features could be gender or race or other things. Then you have other features that are things like zip code, right? And we have some labels given to us that we want to be similar to, some decisions we want to learn to predict, right? These are our labels, but these labels are not necessarily the right labels. They may have some unfairness built into them. They may be labeled by people that have bias when they label things. And so we kind of want to get rid of this. And specifically in this work, we were looking at a type of group fairness called demographic parity. So we would like to find some decision for all of these people applying for loans, for example, that is fair, that is independent of the sensitive attributes, right? We don't want women to pay higher insurance, for example. And the way to do this is you need to actually find what are the latent fair decisions? What are the decisions that were actually the real fair ones that really did not depend on things like gender? And those are not the same ones as the ones we see in the training data, right? And what's also important here is the presence of proxies, right? So it's not sufficient to just get rid of these sensitive attributes and say, I'm going to ignore gender or race, because inside of this feature vector X, there's all these other variables that are strongly correlated with the sensitive ones, things like zip code or education level, okay? And then what we did in this work is train a probabilistic circuit that guarantees that this independence must hold between a latent fair decision, DF, and the sensitive attributes S. While also, of course, trying to explain explain in the kind of machine learning sense of predict the actual observed labels D. And if you do this, then you can compare to other standard tools in algorithmic fairness, you see that you get predictions that are more accurate, meaning more similar to the labels, while also having a smaller discrimination score and having smaller violations of this demographic parity criteria. Okay, so that's all I have time for here for this algorithmic fairness setting, but you can see it's just another way that you want to kind of reason about the behavior of your classifier using the distribution that you have over your feature vectors. All right, so now maybe the most interesting thing we did with probabilistic circuits for this audience, which is around explainability. And so here we were kind of looking at what folks are doing in kind of local explanations. And some of the techniques out there, they are really powerful in some sense, but they're limited in some other sense. And there's a whole bunch of these model agnostic explanations that will try to figure out, which part of your image, for example, is explaining why you're predicting this image as a beagle. Things like Lime, SHAP, anchors. They're great because they treat classifiers as a black box, as very generally applicable. And they evaluate on these sampled perturbations, things like here, I think this is from the anchors paper. Now, the issue with looking at perturbations, and I'm sure this was discussed by others who have more experience in this area before me, the issue is that you can actually evaluate your classifier on things that look like, either complete garbage or really kind of contrived inputs, right? And so knowing what my classifier does on, this is still a very good example from anchors. This is already pretty advanced, but looking at some kind of image where a whole bunch of the image has been grayed out is really not reflective of the feature distribution. And it's not something that my classifier has necessarily been trained on to give any reasonable output, okay? And so this perturbation distribution is kind of, the whole setup is very sensitive to what you choose there. And I'm sure others talk much more about these types of approaches. And so the issue is that, you evaluate this classifier on either completely impossible feature vectors or things that are very low probability, unlikely, kind of nonsensical inputs. And so, what point is there in explaining a function on inputs that don't make any sense, right? So that's the issue here. You have to make sure this makes sense. Another concern could be there's some cool work about how these types of explanations can be fooled adversarially. That's all really cool. There's some work showing that they might be overconfident. And so these are kind of the downsides. They don't really give any guarantees, right? So because of these issues, it's kind of, whatever comes out of the explanation model is what comes out of the explanation model, and you don't really know whether you can trust it or not. That's the downside. The upside is that these are very generally applicable, very useful in practice, right? So I don't want to dismiss these things as being useless. They're actually very useful, but it's a little bit tricky to you have to really know what you're doing. Okay, on the other side, we have kind of recent work on logical explanations. And so you might have seen these as called sufficient reasons, or sometimes called abduction, prime implicants. So that's really cool work because it gives 100% formal guarantees, right? So it's completely the flip side of the earlier slide. They will tell you exactly, if this is what your input looks like, then I would 100% probability guarantee that you will classify this image in a certain way. There's no uncertainty left, right? They give hard formal logical guarantees. They can also, if they want to ensure minimality, this is like the smallest explanation for why this digit is classified as a 1. The issue, though, is that these types of explanations quickly become hard to compute. So, in one of the papers, for example, MNIST is reduced from 784 pixels to 64 pixels, just so that the logical reasoning tool can handle this type of input. Right, and so this is definitely a limitation of the logical approaches. I wouldn't say it's a limitation, but it's kind of like a bug that is a feature of these logical approaches, is that they really don't care whatsoever about the distribution over your features, because it's completely irrelevant. If I want to give a 100% probability guarantee that an image is going to be classified a certain way, I really don't care about the probability of all of these pixels here that I don't know the value of. Right, so for example, here, all of the red pixels are supposed to be black, all the blue ones are supposed to be white, and all of the black pixels and white pixels are supposed to be unknown. And if I observe this image, basically the red and the blue part, I know with 100% probability that this MNIST classifier will say that this is a digit number 1. So it really doesn't matter what the distribution is over these unknown pixels, because whatever it is, you will always predict this as a 1. Now the downside of this is that if you want to give these 100% certainty guarantees, you also need to know almost everything about your feature vector in order to give that 100% certainty. Right, so the explanation here for why this is a 1 involves almost all of the interesting pixels that are in the image, and the border pixels are pretty useless for MNIST, right? It might not look at them. So that's the downside. You get great guarantees, but the explanations may be too complex. They may not actually simplify at all how you understand this classifier. So what we were trying to do is find something in between, and this is what we call probabilistic sufficient explanations. So we would like to not just give these logical guarantees, but we want to give probabilistic guarantees. We want to say that under the feature distribution, meaning for a realistic applicant or for a realistic image, given the explanation, which is again going to be some subset of your features that from the thing you try to explain, the classifier is very likely to make the prediction that you observed. So we want to give these strong probabilistic guarantees that are not 100% always, but on anything that is a realistic input, this is why the image is classified as a 1. And then, of course, we also want these things to be minimal and simple. So there's a little bit more technical details here of how do you actually measure this, right? So here I said we need some probabilistic sufficiency. How do you formally define this? So one thing that you may want to do is use this notion of same decision probability, which says that, given my features z, that this is my explanation, right? These are the pixels that I say are my explanation. If I were to fill in all of these other pixels that I don't know the value of using my data distribution, then what is the probability that my classifier would still give me the same classification as the original full feature vector x? So this is called same decision probability, and it's very similar to the criteria that is used in anchors, at least in principle. And what's nice here is that if the probability here is 1, if the probability of the classifier doing the same thing on the image that was generated from the explanation plus some random imputation of the missing values, if this is always the same, then we're doing the logical reasoning, right? Then we're computing these logical explanations. What's nice, though, is that you can find explanations that tell you that with 99% probability this will happen, and those will hopefully be much simpler. Now, the issue with this definition, even though it's kind of elegant, is that it's computationally very hard. Even on something as simple as naive Bayes, computing this thing is, again, NP hard. So this is not really going to help us come up with this kind of tractable way of explaining things. But there's another kind of notion of sufficiency that we use here called expected predictions. And this is exactly what I showed you earlier when we talked about classification with missing values, right? We're just going to treat the explanation as a feature vector that has missing values for things that are not in the explanation. And we would like to know what is the expected prediction of my classifier. Exactly what I showed you earlier when I compared against all these other techniques for handling missing data at prediction time. Now we will use this as a sufficiency criteria. And what's nice now is that things become tractable. I can do this for logistic regression, decision trees, for all sorts of circuits, random forests, a whole bunch of different, even if I use the probabilistic circuit itself as a Bayesian classifier, I can compute these things efficiently. So that means I can also find these explanations and compute at least their sufficiency score efficiently. Okay, so this is what we'll do. We will find this subset of our features that has the highest expected prediction if we're trying to explain why something was classified as a positive label. You can put a cardinality constraint saying I want a small explanation, find me the best explanation that only uses 10 pixels, for example. If there's multiple of those, you can also just say I would like the most likely one. I want to find a realistic set of pixels that is my best explanation. And that's it, right? Now you can actually run this using some branch and bounce, using some beam search. And here we did this for a decision forest and a probabilistic circuit as our feature distribution. The task is to classify 3s versus 5s in MNIST. And so here you see the explanations that are found for numbers of features going from 1 to 50. And of course, it's always kind of, reading tea leaves with these explanations a little bit. But here, the reason why this was classified as a 3 is because, there's these white pixels here, and there's black pixels here that would otherwise be there if this was a 5, or if this was a 5 that was kind of tilted. Over here, this is classified as a 5 because you have these white pixels here, and then you have the black ones here where you would expect some part of the 3 to be. Okay, and you can also check the expected predictions here. So with this is the log probability of this being a 3, right? So if you just observe the pixels here that are shown in black and white with very high probability, shown by this log probability here, this will be classified as a 3. And with very high probability, this explanation here will be classified as a 5. Okay. Here you have some misclassified examples. So this is a 3 that our classifier misclassified as a 5. And here you see that the reason why it thinks it's a 5 is because it kind of finds this leg of the 5 here, and then a bunch of black pixels that it would expect to be white if this was a 3. Similarly here, this is a 5 that's misclassified, and you can also kind of look at these explanations and try to make sense of them. Okay, so this was kind of more qualitative. So let's look at some quantitative numbers. So here we compare to anchors on MNIST on the full 784 pixels. And the takeaway here is that if you compute an explanation of the same size as anchors, then the sufficient explanations, they're more realistic. They have a higher probability. So the pixels that it finds are actually kind of not kind of crazy pixels. They're kind of high probability ones. So they're kind of it's finding kind of realistic parts of your image to use as an explanation, and it has stronger guarantees. So the expected prediction is much higher. So this means it's just better explanations of your model. And then if you actually increase the number of pixels that you want to use as your explanation to 10, 20, or 30, then you see that these almost become logical explanations. Almost with 100% probability, you will get exactly the same prediction as what you got from your full example. And yet they remain simple, right? These are still small explanations using a tiny fraction of pixels, and they kind of have high probability. This is also kind of an important experiment because this shows that this is kind of a great motivation to take your logical explanations and make them probabilistic. Because here we're saying that that's very simple explanations, meaning high likelihoods, very high up in this figure, still give strong probabilistic guarantees, meaning that this kind of stays very flat for a long time. You can have high guarantees, strong, high value of expected prediction, and still have a high probability of your explanation, meaning that they're very simple, small number of pixels and kind of realistic images. And these figures are very steep around 1 and around 0, meaning that if I take a logical explanation, which needs to be almost certain, and I just make it a little bit probabilistic, it means that I can make my explanation much more simple and have much higher probability. Okay, so this is kind of a call for making these logical explanations at least slightly probabilistic with guarantees. Okay, so that's everything about explainability, and I'm not sure if there's many questions coming, but I may want to just briefly mention this other work here. But again, this would be a great time to ask me about these probabilistic sufficient explanations. Otherwise, I'll move on to something that's just verification of neural networks.
Do we have any questions?
I'm wondering if you've ever tested your probabilistic, well, maybe I'm misunderstanding something, but if I did a model counting on some small example, is your probabilistic sufficient explanation actually equal to the probability or not? I mean, so you tell me that you're using your probabilistic explanation to say, well, there's a 3% chance or whatever.
Right.
But if I did something,
yeah.
If I actually did model counting and just counted the number of actual explanations, is it the same? Is it close? Is it?
Yeah, great question. Yeah. So let me go back here. So how do I know? That actually this number is correct, right? And the answer is you don't, because it's only up to the feature distribution that you've learned. So if you've learned a crappy distribution for your features, then yeah, you will get this number. You always get this number exactly, but it won't actually correspond to your real distribution over inputs that you actually get at your bank. And then this number is not necessarily a good indication. So this all hinges on the fact that you can learn these probabilistic circuits that are very close to the actual data distribution. The model counting idea you give won't actually work because model counting won't tell me how realistic every model is, right? The crucial part is saying it comes here from, like, you know, not all feature vectors are equally likely, right? And model counting won't be able to tell that.
A priori build a probability of my feature vector, give you something, tell you to learn it, then I know the actual probability, I can do model.
Right. If you have a ground truth distribution, then yeah.
I mean, I could do that as an experiment just to check how accurate your claims are. Right.
So the question would be, if I learn a probabilistic circuit from data that is generated from a probabilistic circuit, how close do I get in terms of the likelihood or the... Yeah, that's a great question. We didn't run that experiment. In my experience, I would expect it for a probabilistic circuit because it's so expressive to actually get really close. But that's an experiment we didn't run. Yeah, that's a good question.
We have a question from the audience now because it's hand raised for CPAIOR.
Okay.
You mentioned that your probabilistic sufficient explanations that one criteria is that they should be simple. I just wondered what would happen if you relax this, maybe, because I guess philosophically an explanation doesn't always need to be simple to be useful or even correct, right? I mean, even
that's a great point. Yeah. I mean, also simple is definitely not in terms of like, so here we had the cardinality constraint, right? This is a very dumb kind of notion of simplicity, right? You would like something more about, you know, the cognitive burden on the user, all that stuff. I don't really have strong opinions about this because I don't know how to measure simplicity aside from something like cardinality. Yeah, so I don't have a great solution. If you know of like some formalizations of what simplicity could mean here that are reasonable, or you know,
I just wondered if you have thought about something and just wanted to know.
Yeah, I don't have great ideas about that problem. It seems like something that an engineer wouldn't be able to solve, and you need some other people with other skill sets for that. Yeah, that's a great point. Yeah.
Okay, thank you.
Thanks.
We have questions in the chat somewhat related to the previous one. I wonder if explanations in MNIST, for example, is considered to be reasonable. Understand?
Yeah, I'm not sure what it means. I mean, of course, you know, with all notions of fairness and explainability, they're only reasonable in a very narrow sense, and you can come up with another type of explanation that's reasonable in some other sense. So this is definitely kind of a narrow kind of, I want a local explanation that involves a subset of my feature vector, right? So there's some things here that are arguable, but you know, there's no kind of one way to do these things that I think makes more sense. I'm not sure that answers your question. Yeah.
Roland, does it answer your question? You can unmute.
I was trying to get at that. Would you consider to be an intuitive explanation?
Yeah, that's a good question. And,
no, I understand the technical consideration.
Right. So the question is, does this look useful?
If that is objective.
I mean, so my goal here is to have something that has a formal definition that I know means something. You could, of course, come up with things that look prettier, but may not actually correspond to anything realistic because they don't actually correspond to the real data distribution or the real classifier. And so I would say I'm trying to err here on the side of having something that exactly formally gives you some guarantee, rather than something that may look to a user to be a good explanation, but not actually be informative about the actual data distribution and the actual classifier. Does that make sense? And how to bridge that gap, I don't know.
If you think about information theoretic sense, right, that you might need more than that.
Yeah, good point. So with all of these techniques, of course, there's caveats and caveats of like, yeah, you may want more than this. And we're just trying to build tools that help us get there and help someone look at this and come up with some realization about what the classifier is doing, right? So it's hard for me to kind of make grand claims here. Yeah.
I mean, I'm jumping the gun and sort of going to the user acceptance test, which is maybe very hard.
Oh, yeah. So yeah, that evaluation also we haven't done here. Yeah, we're trying to focus on the reasoning side here, but that's a good point. So I don't know if I have like 1 minute to quickly show you this stuff, that would be really cool. Then
I think let's go for 1 minute. It's interesting.
Yeah, I want to briefly mention this other work, which a lot of you folks are doing verification. And here the goal is to make sure that predictions are monotonic. So often when you learn a neural network, it will actually give these nonsensical things like if you increase your income, then suddenly the amount of loan you can get goes down. And so this shouldn't happen because of monotonicity constraints. And so in this work, NeurIPS last year, what we did is actually use an SMT solver, specifically an OMT solver, to find these maximal counterexamples, things that violate monotonicity, right? So this is a bad prediction, and a counterexample is this one, because the function goes down here and it shouldn't go down. And so very intuitively, what you can do is you can replace each prediction of your neural network by its maximal counterexample. And then what you get is something that looks like this. You get some kind of monotonic envelope of your neural network. And this one is now guaranteed to be monotonic. And it works also for high dimensional input and feature vectors. And so this is something which I think is really cool, because you can also then find counterexamples during training using your SMT solver and give it to your neural network learner, and use monotonicity as an inductive bias. And so the reason why I think this is cool is, there's a lot of talk about neurosymbolic learning and verification of neural networks, but very often I find that, it's a little bit detached from the actual kind of, bottom line performance of the classifiers, right? It's more conceptual work. And this stuff actually works really well, right? This is just an SMT solver helping the neural network, and you get state-of-the-art results in monotonic predictions. You do better than these neural networks that are specifically designed for this task. So this is really a great combination of kind of reasoning and neural networks that I find pretty exciting. So yeah, please check out this work. You can simultaneously get provable guarantees. With 100% probability, you will never violate monotonicity when you make these decisions, and you won't get sued by your customers. And at the same time, you actually improve your accuracy, right? So it's not like either or, it's actually both of them. And so I think this is pretty exciting. Just wanted to mention it. And so yeah, that's just the end of my talk. And I should thank all my collaborators, of course.
Thank you, Guy.
All right.
I think we're a little bit out of time. Maybe if someone has one or maybe one quick question, we can still. Did you have actually any scalability issues with SMT solver when you were finding counterexamples?
Yes, good point. So these counterexamples, they're a little bit tricky to find. So yeah, for large neural networks, you will have to, you won't get the answer. What's nice here is if you want to find monotonicity counterexamples, actually all of your inputs, except for the monotonic features of your neural networks, are actually fixed to a constant. So it's actually strictly easier as a reasoning task than a lot of the other verification tasks. And that allows us to make it quite a bit more scalable. And so, for example, these data sets that we tried on, these are not kind of simple, contrived, like downsampled, simplified data sets. These are the real data sets that people have evaluated on in this particular subfield of machine learning. So I would say it won't scale to ImageNet, but it will scale to whatever people care about in this field to be the realistic data sets. So that's nice for the SMT solver community. Yeah.
Thanks. Okay,
All right,
we thank Guy. Thanks a lot. Very nice talk.